Hello everyone, welcome to this brand new unit of chemistry. Today we will be talking about equilibriums. The topics that we will be going over includes ice table, the shifting of the graph by using the Le Chatelier principle, the equilibrium constant, and the solubility. Let's begin by defining what is chemical equilibrium. It means that the forward and the backward reaction speed are the same, so no visual change will be observed. And it is very important to keep in mind that it doesn't mean that the reaction is stopped from happening. It just means that the forward and the backward reaction have the same speed. So they just cancel each other out. It doesn't mean that the reaction is completely stopped. So here is an example. Excess sodium chloride is added to the water. When the solution gets saturated, the speed of the dissolving and the precipitating are actually the same. So the precipitate amount is neither increasing or decreasing. Here is a typical form of equilibrium reactions. You will see this two-way arrow pointing away from each other. And the equilibrium state of a reaction will eventually be reached, but it might have different speed. So it begins from happening fast. It has a greater difference of the forward and backward reaction. And eventually, when the equilibrium state is very close to being achieved, the speed will be slowing down as the concentration of the reactants or the product, the one that's in excess, the concentration has been decreased. So here they have the same speed, the forward one and the backwards one. And let's take a look at the one example of the equilibrium graph. So this is our sample reactions, and those dashed lines are going to be the equilibrium states of each of the reactants. And the equilibrium can be established from both sides. So what it means is that if the product is the one that being accessed, then the product will be decreasing and the reactants will increase. And on the other hand, if the reactants are accessed, then those reactants will decrease and the product will be increasing. And eventually both of those two scenarios will be reaching the same equilibrium state. So here, this is how does the graph will look like if the equilibrium state is coming from the reactant side. As you can see, the reactants are being decreased and the product will be increased. And on the opposite side, we can also decrease the amount of product and increase the amount of reactants and achieving the equilibrium states. And one thing to keep in mind that the change of the concentration of one is with respect to one another. In this case, for each 1 mole of H2 and I2 being consumed, 2 moles of HI will be produced. So the change is also going to have a double ratio with each other. This one is 2 times of this. This one is being consumed. The amount that's being consumed is 2 times as the amount being produced of H2 and I2. Now let's talk about what is ice table. So ice table is a table that's being used to determine the equilibrium state of a reaction, given one of the final concentration of either the product or of the reactants. And we need to fill out the rest of the table based on the information that we are given. So ice table, I stands for initial concentration, C stands for the change in concentration, and E stands for the equilibrium concentration of each substance. Here is a very simple example of ice table. We go over initial concentration for each of the substance and the change and the equilibrium concentration states. So the initial plus the change is going to be the final one, which is the equilibrium state concentration. And the change also follows the stoichiometry ratio. In this case, we have 1, 1, 1. So the change amount for each of those are the same as each other, are equal to each other. And also we notice that the ending equilibrium amount is not necessarily the same as each other. So this one is 0.6, this one is 0.4. So it's not like in physics, if we want an object to be at equilibrium state, we need to have all kind of force to be canceling out each other, and they need to cancel out to be equal to 0. But that's not the case in chemistry. We could have one side have slightly more reactants than products. We could also have the opposite, that we have more products than the reactants. And let's do some practice with the ice table. So typically you are given the initial concentration of all of the chemicals, and you will be given one of the ending amount of the product or the reactants. And what we need to do is to fill out the rest of the table. So here, the first step is to determine one of the change in concentration for a substance. We are given the initial and the ending concentration of the reactant B, so we can calculate how much has this change in concentration. So we simply have the ending amount subtract the initial amount, we got a change. And once we obtain that change, we use the stoichiometry and finding the ratio of all these substances. And once we determine all of the change in concentration, we go back to the initial table and calculating rest of the ending concentration of these. Okay, and how do we calculating the ending amount is by having the initial amount plus the change. That's going to give us the ending equilibrium state or concentration of the chemical. Now let's try another example. So in this case we get another reactions, and as usual we get our initial concentration and one of the ending concentration. So first step, we determine one of the change in concentration. In this case we're going to calculate A2, and then we use the stoichiometry and finding the ratio of the change, that's change in amount of the other two chemicals. And we then calculating the ending concentration of the other two chemicals. Let's take a look at the Le Chatelier principle. So the Le Chatelier principle states that when a change is being made on a equilibrium system, the system will shift in a way that counteracts the change. And one thing to keep in mind is that the change in concentration only applies to change the concentration of gas and the ion substance. We don't care about solid. If the solid change in amount, it doesn't matter, okay? The solid has no effect. And let's take a look at some of the typical type of change we will get for the Chatelier principle. The first typical one is the concentration. So here, if we increase the HCl, the hydrochloric acid, the system will shift to the right to use up this excess HCl. And notice that this HCl is aqueous, which means that it is an ion. So this does apply. If this is a solid, it doesn't matter, because solid, it just won't react and change in concentration. And let's take a look at temperature. So here there are two different scenarios. It depends on whether the reaction is exothermic or endothermic, and you write the heat on the corresponding side. Remember, if this is endothermic, the heat will be showing up on the reactant side. If this is exothermic, the heat will be showing up on the product side. If the temperature increase, the equilibrium in this case will shift to the right in order to use up this extra heat. And then we have dilution. If water is added to the system, then the concentration of the ion will actually decrease. So in order to replenish that, the solid AgCl will be used up. The equilibrium system will shift to the right to produce more ions. Now here comes a very tricky one, pressure and volume. So here we got a reaction between gas molecules. If the volume of the container increase, then the equilibrium will shift to the left. In this case, because it will produce more gas molecules to fill up the space. The other way to understand this is that if the volume is increased because of the decrease in pressure, then the equilibrium will increase in pressure to balance out the missing pressure, okay? Here, it is very tricky when the pressure is increased or decreased, because it depends on the type of the container. There are two different types of the containers. One is called a rigid container and the other is called a non-rigid container. As the name suggests, the rigid container will not change the volume of the container if the pressure changes. However, on the other side, if the non-rigid container experiences a change in pressure, the volume is going to change correspondingly. If the pressure increases, it will squeeze the non-rigid container and decrease in volume. And it is also vice versa. If you decrease in pressure and allows the non-rigid container to expand, that will increase in volume. So we need to determine whether the container is rigid or non-rigid before we make a judgment. So here, if the pressure increase, if this is rigid container, it will have no change in volume. No change in volume means no change in the equilibrium. However, if the pressure increases and this is a non-rigid container, the volume will decrease and the system will shift to the side where there's less gas molecules, which it will shift to the right to accommodate the change in the volume of the container. Now let's do some practice, because this is very common in the AP exam multiple choice. So I prepared a lot of exercise to make sure that we truly understand the concept. So here we got a reaction. So what will happen to the equilibrium if the following happens? The first one is if UO2 is being added. So the first thing first is if something has a change in concentration, we need to determine whether it is solid, whether it is aqueous, whether it is a gas, whether it's a liquid. So here, we can see that this thing is a solid, so it has no effect on the equilibrium. So we only care about ions and gas, we don't care about anything else. Okay, as the concentration of those is not going to be changing. And the second one is if if HF is being reacted and used up with the gas. So this thing is decreasing in concentration. The equilibrium will shift to the left to replenish the missing HF. So we have talked about Le Chatelier principle, talks about if there's a change on the equilibrium state, then the system will shift in a way that to counteract the change. So this is decreasing, so the system will shift to increase it. The last one is water is being removed. So this is a gas molecule, this thing is getting removed, so the system will shift to the right to replenish it. Now we have another chemical reaction. The first one, if CO2 is being removed, so it will shift to the right to replenish it. Okay, the second change, if this is a rigid container, it doesn't matter that if the internal pressure is increasing or decreasing, it has no effect because there's no change in volume. And the third change is with respect to temperature. So if the temperature increase, assuming the exothermic reaction, we write down the heat either on the product side or on the reactant side, depends on whether it is exothermic or endothermic. Exothermic is appear on the product side. Now, since we figure out which side this heat term is on, now we can make a decision. So the temperature increase, then in order to use up this excess heat, we will shift to the left to reduce the heat. And lastly, if the volume decrease due to a increase in pressure, what is the effect of the equilibrium? If we take a carefully look at the reaction, here we will observe that there is a equal amount of gas molecules on the reactant and the product side. Therefore, it doesn't matter which way you shift, the partial pressure produced by the system is the same. It doesn't matter where you shift, it will have no effect, according to the ideal gas law. So it has no effect on the equilibrium system. If there's one side with more gas molecules and one side with less gas molecules, then the equilibrium will be shifted to the side that has less gas molecules. But that's not the case here. We have our third equation over here. The first change we made is if we add a argon gas to the rigid container. So this type of gas that's not being react with those chemicals inside our chemical reactions is called inert gas, which suggests that it doesn't participate in the chemical reaction, but it does change the internal pressure of the container. Since this is a rigid container, it has no change in the volume, even though the internal pressure is increased. Therefore, it has no effect on our equilibrium states. The second one is the volume is being doubled. So the volume is increased. The equilibrium system will produce more gas molecules. However, there's equal amount of gas molecules on both sides. There's no side such as there's more gas molecules. It has no effect on our equilibrium system. And finally, the temperature decrease, assuming this is exothermic reaction. Since this is exothermic, we write the heat on the product side. And the heat is being decreased. we will have the equilibrium system to shift to the right to replenish the heat that's being lost. One more thing about catalysts is that catalysts speed up the establishment of the equilibrium position by increasing both the backwards and forward reaction speed, but it doesn't really change the equilibrium position of the reaction. It only changes the speed. And now let's take a look at the graph for establishment of equilibriums when it encounters one of the changes below. The first one is the concentration. For a change in concentration for a single species, you will see a sharp increase or decrease for one of the species, while the others remains very change slowly, and it's like a continuous curve. However, on the other hand, if we are changing the temperature, all three of them are changing slowly. So no sharp turns in this case. If we increase the pressure or change in the volume, all three different substances will have a sharp increase or decrease, because the changing in pressure is like very fast, and it's at this moment the volume changes, but the amount of the substance is still remains the same. So at one moment, the concentration of all the reactants and products are being changed immediately. So there are three different sharp turns in the graph. Let's talk about what is equilibrium constant K and the reaction quotient Q. So in general, the equilibrium constant K for these type of reactions is expressing as this. The products on the top of this fraction, and the reactants are at the bottom of the fraction, and they are all raised to the power of its original coefficient in the chemical reaction. For the equilibrium constant K, we only care about ion and gas molecules inside the reaction. If this is solid, we don't even care, because increasing in amount doesn't really change the concentration, so we don't even bother it. And one more thing is that we don't really talk about the unit for K, and you will never see a question asking you to state the unit in the AP exam, so you don't need to worry about that. And another thing is equilibrium constant only change when the temperature changes. When the pressure changes, when the volume changes, when catalyst is added, all those doesn't matter. The only thing that changed the equilibrium constant is the temperature. And so the only difference between the equilibrium constant K and Q is that the concentration that they are using. K is the concentration of the reactants and the products at the equilibrium states. However, the reaction quotient is the concentration of the current state of the reaction. They both have the same formula. The only thing that's different is the concentration that they are using. Q is measuring how much, to what extent the reaction has been finished, and the K is like the final position that the reaction should be in. If Q is less than K, based on this formula here, we can see that the concentration of the product here for Q must be less than K, and the denominator, the reactants, must be higher. So there's more reactants than it should be at the equilibrium state. The reaction will shift to the right side to produce more products and use up reactants to make Q equals to K and complete the reaction. And on the other hand, if Q is greater than K, that means there's more products than the reactants comparing to the equilibrium states of the reaction. So the system will shift to the left to use up the excess product and producing the missing reactants. There are many types of equilibrium constant K, and you might see a lot of other different during this chapter of study. For the default version, K, Kc, and Keq, they are all interchangeable, and in terms of concentration, when I used to calculate the equilibrium constant K for the in terms of concentration, and these are some special version. A, B as for the acid and base, we will be studying this in the next chapter. And W is for water, also you will be learning this in the next chapter. KSP, we will be learning this at the end of this video. They are all using concentration. If you see Kp, that's the equilibrium constant K for the partial pressure. For this one, you will be using the partial pressure for gases. But the calculation process is the same as the concentration, but now we are just using pressure instead of concentration. Let's talk about how does temperature affect the equilibrium constant K. It depends on whether the reaction is exothermic or endothermic. The exothermic reaction, you can see that the heat is over here. By applying what did we learn 10 minutes ago? We can know that the equilibrium will shift it to the left if the temperature is increased to use up this excess heat. And at the same time, as it shifts to the left, the concentration of C will decrease and the concentration of A and B will increase. So the products are being reduced and the reactants are being increased. The overall K is getting decreased. On the other hand, if this is endothermic and you raise the temperature, the equilibrium will shift it to the right. No, shift to the right. Shift. Okay, shift to the right. And the opposite will happen and the K is going to increase. There are 3 different simple exercises for you to practice. We are given 3 different equations and we need to write the equilibrium constant K in terms of the concentration of the chemicals that's inside the reaction. First, we observe that this is a solid. We don't even need to consider about this. The product raised to its power of the coefficient and the reactants at the bottom. And we get our first question solved. And exercise number 2, again, this is solid, so we don't care. For those of you who don't know, this is a special type of K, the equilibrium constant. This is the KSP. This is the solubility equilibrium constant. Again, we just do the same thing. We talk about that we only care about ions and gases, and for the ions, we just do the same thing. Since there's no reactants that are in gas or ion states, there's no need for us to add anything at the bottom of this fraction. And that's going to be our equilibrium constant. Exercise number 3. This one is also very easy. They are all gases. The products, we raise the power of its coefficient. And the reactants, we put them at the bottom. Now let's talking about how to manipulate the coefficient of equilibrium constant K when you are giving a series of reaction. Each was given the equilibrium constant K for each reaction, and you need to find the equilibrium coefficient K for a bigger reaction. There are some basic arithmetic rules that you need to remember over here. The first one is when you are reversing a reaction, the equilibrium constant K is being flipped. So it's going to be the inverse of the original equilibrium constant K. as indicated in this example, if this is our original reaction, and this is going to be our equilibrium constant K, when we flip it, the equilibrium constant K is also going to be flipped. If you don't believe this, you can actually try to figure out the equilibrium constant K just by looking at this equation and also this equation and compare. You will see that this is indeed a general pattern for this. The second rule is the addition of the reaction, like what we did back in Unit 6 for the Hess's law. When we are adding the different reactions, the equilibrium constant K are actually multiplying each other. Let's take a look at this. We are given two different equilibrium reactions, and those are their equilibrium constant K. Okay, and then if you trying to figure out the equilibrium constant K for this reaction, it is this. What you are noticing is that this thing here is actually the product of K1 and K2. Lastly, it's going to be the change in the coefficient of the chemical reaction. If this is our original reaction, this will be our rate constant K expression. If we change the coefficient for each substance, let's say divided each substance by 2, the coefficient, then the equilibrium constant K is going to be to the power of 1/2. If this is our new equation, the equilibrium constant K is going to be raised to power by 3 compared to the first equation. Once you remember that, you can now apply this to get a equilibrium constant K for a brand new reactions without knowing the actual equilibrium constant K for each reaction. I don't know how to explain this, but this is quite often being showed up in the AP exam, and those are just the rules that you need to remember for quickly calculating the new equilibrium constant K. And there's something that you need to know is that the thermodynamic favorability for the equilibrium reactions, if the constant K is greater than 1, then it means that equilibrium constant K is thermodynamically favored. If the K is less than 1, then the delta G is greater than 0. It is thermodynamically unfavored. Here, this is the formula. It doesn't show up quite often, but it's just very good to know when you are studying for the AP exam. R here is the ideal gas law constant. T is the temperature in Kelvin, and the long K is the equilibrium constant. And it is always also very easily to be understand this formula. If K is greater than 1, that means it is product favored. That means we will be producing more product by the default of the equilibrium rules. If this is less than 1, that means the forward reaction is unfavored. That means you need to help it by adding some kind of substance to keep the reaction going. It's not equilibrium favored. That's basically what this formula is saying. Let's do some examples. Here we are given two different reactions, and the K is given for each of the two reactions. What we need to do is to express this reactions by using K1 and K2. Notice that PbCl2 is only showed up in the reaction number 1. Therefore, the reaction number 1 must be exactly 1 times for the net reactions, and AgCl, and it is raised to a coefficient of 2. We correspondingly just flip this formula and multiply this by 2. This is how we get a net reaction, just like what we did in the Hess's law, applying the rules that we just learned, how to manipulate the coefficient K. Remember, adding one reaction is multiplying, and subtracts it's just reversing the original equilibrium constant K. The coefficient here just raise it to the corresponding power, and we get our new equilibrium constant K. Here is a second example. As usual, we are given 2 different reactions. The first thing here is just apply the Hess's law and figure out how do we use those 2 reactions to get the net reaction. Then what we need to do is apply the rules what we learned in the previous page. Reaction number 1, we just multiply K1. Reaction number 2 is minus, so we flip it and then multiply it, and we get K1 over K2 to be our new equilibrium constant K. Let's talk about some basic types of equilibrium calculation you will see in the exam. The basic substitution. We are given the concentration for each species when it is at equilibrium. We also know the reaction expression, thus we can figure out the equilibrium constant K expression. We just need to sub in the value and we get the equilibrium constant K. This one, okay, so this one is just for gases, and we use the partial pressure for each gas substance and subbing into the formulas. We can calculate the Kp in this case. Now let's make it slightly more difficult by involving the ice table. In 1 liter container, 0.5 moles of this, 0.5 moles of this are being mixed, and at the equilibrium 0.2 moles of NO2 is found. Calculate the Kc. We are given the chemical reaction. The first thing we will be doing is to use the ice table and figure out the amount of each substance that's being changed. The first one and the second one, they are the starting amount for each of those substances. Notice that there, although this is not being mentioned in the question, but NO2 we are starting with none. We know the ending not concentration, but okay, you can say concentration of the NO2. We apply what we usually do with the ice table. We just fill this out following the order. First, calculate one of the change in difference, use the stoichiometry ratio, then calculate all of the ending amount for those. Now we can just substitute all of the concentration into the equilibrium K expression and calculate the equilibrium constant K. Now we are doing something slightly different. We are given the equilibrium constant K. We now need to do the opposite and finding the concentration of all of the substance at the equilibrium. In this case, what we will be doing is to set up some variable and expressing the concentration use those variables and solving quadratic or linear equations, and then plugging back the value of x and calculate the final concentration. If we are assuming that the change amount for the first two is x, and then this one will be increased by 2x, we now have expression for each of the substance at equilibrium. We sub into the expression of K. We got K in terms of X, we are also given the exact value of the equilibrium constant K in the question. We equate these two things equals to each other and just solving for X for some kind of equation, and we get a value of X, and we subbing back and we subbing this back into the expression, and we can calculate each of the substance to the exact concentration. Now, don't forget to check your answers. You can sub in the values for 3 substances back into the equilibrium K expression, and just making sure that this is equal to the one that's given in the problem. And you can be fairly sure that you are getting the correct answer. There's also one additional type of problem that you will see, is that originally we are at equilibrium, then a change will be made. What we need to do is to be calculating the new equilibrium circumstance given the original equilibrium. Here, the first thing first is that we can calculate the equilibrium constant using the original concentration by writing out the expression and subbing the value, and we get the equilibrium constant K. And just mentioned before that the equilibrium constant K will only change if the temperature change. So if pressure, volume, and concentration, those things being changed, the equilibrium constant will not change. And we set up our ice table for the new equilibrium, and we subbing that into our equilibrium constant K expression, and we get K in terms of X, and we, as usual, we equate those two things together, the expression and the value, and we solve the equation and calculate the value of X, and sub that thing back into the original ice table final value, and we can calculate the concentration for each substance. We will now talk about the solubility. Usually, solubility can be expressed in a variety of different units. You can see mass per volume. You can also see the most amount per volume. In this chapter, you are most likely to see the most amount per volume. That's very standard. The official definition of the solubility is mass per volume dissolved in a given amount of solvent, the liquid, to form a saturated solution, which means you cannot dissolve any more of the solid into the solvent at a specific temperature, because the solubility will change according to the temperature. The temperature gets higher, more of the solid will be able to dissolve in the solvent. The temperature likely you will see in this chapter is going to be at 25 degrees Celsius. That's the standard condition, the 25 degrees Celsius and the 1 atmosphere pressure. There's a simple rules that you need to remember for classifying what substance is soluble and what substance is not. The group 1 element, the alkali metals like sodium and potassium, those are always soluble, and the ammonia ion, they are also soluble. KSP, let's talk about KSP. KSP is an equilibrium constant that allows us to calculate the molar solubility for a substance under the standard condition. The pressure and the temperature, as we discussed before, should be 25 degree and 1 atmosphere temperature. The solution by default is going to be water. Thus, none of the ion has already been existing in the solution. And also remember, KSP is for the insoluble substance. For the soluble substance, the KSP is going to be extremely large, and it doesn't matter how much you put in, most likely it will be getting dissolved unless you put extremely huge amount. We only discuss KSP for insoluble substance to a certain places after the decimal place. Let's talk about how do we express the KSP. As recalled from previously, the K equilibrium constant depends on the gas molecule and the ions. We will only be discussing ions here when considering the equilibrium constant K. And the formula here is you gonna raise the power, raise the coefficient of the power for each of the solution ions to the concentration to those powers. Let's see one of the example to help us to better understand how does it work. The lowercase a and b, they are going to be our subscript and a part of the compound formula. The capital A and B, they are the actual element. And this is a very typical expression for the equilibrium expression for dissolving. As you can see, the subscript now becomes the coefficient. And those are the ions being separated. This is our old friend ice table. We're gonna assume that originally there's a very huge amount of the solid, and we keep dissolving and until a certain moment that we can no longer dissolve. The rules of the stoichiometry ratios also holds here. This is going to be the concentration amount for the for each type of the ions. You raise them to the power of their coefficients, and that gives you the value of the KSP. Let's see one specific example is the silver chromium chromate. And we just follow the rules. We put the subscript to become the coefficient. Then we have each type of the ions, and we use the ice table to calculate the ratios. And then we get the ending amount for the KSP. KSP expressions in terms of X. Here we assume that X is the amount that's being used up for the original solid. Now we can express KSP in terms of X. Typically you will be given the KSP and you need to determine its molar solubility. We have a expression for X and a constant, and we just need to solve for the equation. We can get the amount for X, and that's going to be our concentration. Let's do a second example. We do the same thing, just write down the equation and making our ice table and finding the ending concentration and raise them to the power of their coefficient, and we get the expression in terms of X, and this is our KSP value. Now we just need to solve the equation. We divided 27 and take the root of 4 for this number, and we get the molar solubility. You can also do the opposite, where you are given the molar solubility and calculate the KSP value. We now use our ice table, and we can directly calculate the concentration for each of the ions, and we raise them to the power, and we combine the terms and getting the KSP value. Let's talk about one of the exceptions that we'll be facing, which is called the common ion effect. This is an effect where one of the ions are already in the solution. We are now no longer dealing with pure water, which assumes that there's nothing special there. One of the ions has already been here, and that's called the common ion effect. That's going to reduce our molar solubility of the substance because the KSP value will build up in much more quickly, and there will be less space for the substance to be dissolved. First, let's try to find the molar solubility for this substance, for this solution over here, and we are given the KSP value. The magnesium chloride is soluble substance, so it will completely dissolve. We've used our ice table here, and we can find the concentration amount for the two types of the ions. We carry this magnesium ion amount here when we are dissolving the magnesium hydroxide. And now we still use the ice table, but we have a slightly different expression for x. Here we get 0.2 plus x instead of a single multiple of x to a certain power. We still proceed as usual. We write the equilibrium constant expression. We get a expression for x and a constant. We just need to solve this equation, but you will realize that there's a slight problem because this is a cubic equation. It's kind of hard to solve. One key insight that we will be making is that this number is extremely small, which means x should also be very small. A number plus a small number is going to it's just going to be equals to this big number. You can just ignore the x, but if you are multiplied by a small number, you cannot ignore that. So we simplify this to 0.2 times 2 to the power of 2x to the power of 2. We just need to solve this, and we get the molar solubility like we did before. Final type of question that you will be seeing is to compare which ion will precipitate first. Let's take a look at this example. We have a solution that contains 0.001 moles of silver plus ion and 0.1 mole of strontium, if I remember correctly. But that's not the point here. And the job here we need to do is to compare which one is going to precipitate first if a certain substance is slowly being added. It doesn't matter if we add this or not. The concentration for Ag plus ion and Sr plus 2 ion is not going to change. The only thing that will be changing is the chromium concentration. Now what we're gonna do is to use this KSP value and write the expression and sub in the ion that has the fixed concentration, and the other one is going to get slowly added. The only thing we need to do is to compute the concentration for the chromium ions that's needed for a certain precipitate to form. For example, the silver one, we first sub in the KSP value and divide it by the Ag plus ion concentration to the power of 2 based on the equilibrium constant K rules. We need to raise them to the power of its coefficient. And we find the concentration for the chromium ion that's being needed. For this, the second precipitate, we do the similar thing and get the chromium concentration. Now what we're gonna do is to compare those two values. The one that needs the smaller concentration of chromium ions is going to precipitate first, because that one will have enough concentration to hit the KSP limit and form the precipitate. And that's all for this unit, and see you in the next one.